Okay, so we've talked about how to undo chain rule with integration by substitution or use substitution. We've talked about how to undo product rule by integration with parts. We now need to discuss how do we undo quotient rule. And that's going to use a process that's called partial fractions. And I'll have a later video that builds on the partial fraction work to an application, which will be our next unit, called logistic growth. So partial fractions are a way to unadd fractions and break it up into a sum of easier fractions. To do this, the degree of our numerator must be less than the degree of the denominator. So much like with substitution, we might have to do long division to get to this point. So I'm not going to focus on the calculus here. I'm going to focus on the algebra part of partial fractions, because partial fractions in and of themselves is not calculus, it's algebra. So the idea of this is if I have a rational expression like x minus 13 over 2x squared minus 7x plus 3, the first thing I want to do is I want to factor the denominator. So yeah, I have x minus 13 on top, 2x, x minus 3 minus 1, so 2x squared minus 3, or minus 6, minus 1, minus 7. Yep, that works. Now, however many factors that I have, this is going to be the sum of those factors. I could have just 2 like this. If I had 3 factors on the bottom, there'd be a third fraction that I would add on. But the problem here is I don't know what my numerators are, so I'm just going to put variables up there. For partial fractions, we tend to use capital letters, A, B, C, D, E, and so on. Now, if the denominator of each of these fractions was not linear, it gets more complicated, but in terms of AP calculus, it's always going to be linear denominators. And the goal here is I need to figure out what's A, what's B. So the easiest way to do that is for us to say, let's not have fractions. So I'm going to multiply my entire equation by the common denominator of the 2x minus 1 times x minus 3. And since I'm doing this to both sides of the equation, this is allowed. So I'm going to have x minus 13 equals a. The 2x minus 1 would cancel, so times x minus 3, plus the b, and the 2x minus, and the x minus 3's cancel, so 2x minus 1. I then want to know what would make my denominator 0. So for the a, the thing that would make the denominator 0 would be x equals 1/2. And for the fraction with b, its denominator would be 0 when x equals 3. So I'm going to see what happens to my green equation when I plug those two x's in. So if x is 1/2, what I get is 1/2 minus 13 would be negative 25 halves. Then I had a, then 1/2 minus 3 would be negative 5 halves. So then I could solve this for a, and then b times 0 is 0. So solving for a, I would get that a is 5. If I plug 3 in for x in the green equation, I would have negative 10. A times 0 is 0, plus b times 2 times 3 is 6, minus 1 is 5. So b is negative 2. So what this means is that I now know what a and b are. So my original fraction, x minus 13 over 2x squared minus 7x plus 3, is equal to a over 2x minus 1 plus b over x minus 3, which, if I needed to integrate, gives me easier integrals. So if I now look at, well, let's go ahead and do the integral of this. Partial fractions doesn't evaluate the integral for me. Partial fractions gives me easier integrals to calculate or to evaluate. Again, this is not something that's common, so this is like a last resort. 95% of the time, we're going to know the antiderivative directly. 3% of the time, it's going to involve chain rule and be integration by substitution. Then it's either going to be 1% integration by parts or 1% partial fractions, product rule and quotient rule. So we're going to end up with smaller integrals that will probably require integration. Just as a heads up, you're going to see tons of natural logarithms when we do partial fraction problems. So we already did the partial fractions for this. One, I don't know anything that has this as its derivative, so I don't know the antiderivative directly. If I set u equal to 2x squared minus 7x plus 3, I know I'd have a 4x minus 7 in its derivative, which isn't going to cancel out the x minus 13. So substitution's not going to work. That doesn't look like a product, so I'm not going to try product rule, which means it's quotient rule. So quotient rule means that I know that this is going to be the same as the integral of 5 over 2x minus 1 plus negative 2 over x minus 3. And remember, I can break that up into two integrals because of my sum and difference property for integrals. And now I can do these as two separate integrals. With the integral of 5 over 2x minus 1, I don't know that directly, but I think 2x minus 1 is inside of something. So I'm going to try substitution. So this would be 5/2 the integral of 1 over u du, which is 5/2 times the natural log of the absolute value of u, which would be 5/2 times the natural log of the absolute value of 2x minus 1. Again, I'll save my plus c for the very end of all of my work here. If I focus on the negative 2 over x minus 3, I don't know that one directly. So I'm going to try substitution. So I'd have the integral, negative 2 times the integral of 1 over u du, which is negative 2 times the natural log of the absolute value of u, which is negative 2 times the natural log of the absolute value of x minus 3. So from all of that work, I get 5/2 times the natural log of the absolute value of 2x minus 1 minus 2 times the natural log of the absolute value of x minus 3 plus c. And there is my antiderivative. So to get one more example of this in, if I have the integral of 2x cubed over x cubed minus x, I do not know the antiderivative. I do not know anything that has this as its derivative, so I don't know the antiderivative directly. If I say u is equal to x cubed minus x, that means I'm going to have a 3x squared minus 1, which is not going to cancel out. So substitution's not looking good. It's not a product, so I'm thinking quotient rule. But to do partial fractions, I have to have the degree on top smaller than the degree on the bottom, and they're equal right now. So the 2x cubed over x cubed minus x, I could simplify a little bit, because that's 2x cubed over x times x squared minus 1. So that's 2x squared over x squared minus 1. Still can't do partial fractions on that, so I do need to do some long division. So what would I multiply x squared by to get 2x squared? Well, a 2. So 2 times x squared minus 1 is 2x squared minus 2. But I subtract all of that. The 2x squareds cancel. Nothing minus a negative 2 is a positive 2. And that's going to be my remainder. So this is going to be the integral of 2 plus 2 over x squared minus 1. Well, the x squared minus 1 I can factor. So now with into x plus 1 and x minus 1. So I can do partial fractions. Multiply by the common denominator. What would make my denominator 0? So if x is negative 1, and if x is positive 1. So if x is negative 1, I get 2 equals negative 2a plus 0. So a is negative 1. If x is positive 1, I get 2 equals 0 plus 2b. So b is a positive 1. So this is now the integral of 2 plus negative 1 over x plus 1 plus positive 1 over x minus 1. Antiderivative of 2 is 2x. And I have the negative 1 times the natural log of the absolute value of x plus 1 plus the natural log of the absolute value of x minus 1 plus c. And there is our answer.